So being total amateurs, we're just going to repeat what we just already said before starting recording, right? Is we were lamenting the loss of maybe a better Twitter that may have existed only in our minds, or actually have existed like 6 to 7 years ago, where there's a new paper in psychiatry, then everyone would discuss it, and there you'd meet new people who had very different views of psychiatry from you, and sometimes it would be productive, sometimes it'd be a shouting match, but invariably there'd be like 7 opinions you'd learn from in threads and counter threads and all that, and it could be very productive, and that's kind of lost. And so as a stand-in, me and Eiko, I think we go back quite a while, because when I was a PhD student at the VU in Amsterdam, you were a postdoc at the UvA in the lab
Nice.
where I did my masters, and I think we met at a talk somewhere there. We've been going back and forth on many things related to psychiatry and genetics, because I do the genetics of psychiatry and you do psychological sciences more broadly, and that's the thing we discuss frequently.
And
Either
it's nice
well,
to talk to you every, year or 2 years or every 2 months over a coffee about this and related topics.
right.
And
And now
it's
we're
also
actually even
oh,
trying to write papers, though, that's still like
exactly.
the student working with us is going to see this and going to be like, why are you spending this hour not working on my paper, but discussing a different paper? And we're sorry, Natalia, we'll get to your paper. Just not today. And the thing that triggered me actually for this one discussion is that there's a new GWAS out for depression. It's over 650,000 people with depression as cases, and we'll get to like whether that's actually the number we believe is true or not. And then 4.3 million controls, which is a staggering number. It's like all of Belgium, or maybe Flanders, or mid-sized European country basically in terms of controls. And there are case and controls from all over the world, from basically any ancestry, and that's new in GWAS. That's actually a great thing. But I also know a lot of people are very critical of GWAS, or haven't been keeping up with GWAS, and have frequently asked me like, why do we even need millions of people? So that's sort of like, yeah, it's a hot button topic in our field, and it's sort of like hard to pinpoint what the use of GWAS is anyway. And it's sort of like, I mainly feel like the people doing GWAS are slowly, because it's like an art in and of itself, drifted away a bit from all the other people in psychiatry. And it's sort of, I think these things can help us get back to a common ground, I guess. That makes sense.
Yeah, it makes sense. I think it would be nice to then spend a few minutes on generally what is GWAS. With that I don't work in this field, but I'm really interested in depression research, measurement theories and so forth. I haven't always been super happy how things were done in this area, perhaps. And you have worked in this area for quite some time. I've been on a number of bigger papers as well. Are you co-author on this one as well? Or?
No, I'm not. No, that's why I felt like comfortable discussing this. It's still a preprint, and for people watching along, it's on medRxiv, which is a medical archive site, and it's a genome-wide study of major depression in 680,000 diverse individuals, identifies 700 independent associations. Blah 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 blah. Long title. If you type GWAS depression, you're going to find it in medRxiv, and I'm sure if this thing will have a thing where we can share links, I'll include the link. I'm not on this one. It's not published yet. It's a preprint, and so journals are skittish about any kind of anything prior to publication, especially by authors, right? And so I felt it would be not great to discuss it with an author. I'm not an author, and I want to jeopardize his chances at journal. It's not collegial of me to do so. Therefore, we can discuss it. None of us are authors on it.
Yep, and I think both of us could have
brief GWASs.
Both of us have friends on the paper, I'm pretty sure. So, we're gonna. Yeah. It's also interesting space to discuss the paper.
Yeah, I mean, we're close, but we're not on it, so we're free to sort of discuss this one.
So, do you want to start the roundup for? So, I'm going to talk about to you about it as an expert today, but I will talk to the potential audience as people with maybe my background. They have heard about what genetics is, but they don't, caught up on the literature too much. Some of them might be academics. Some people might be sort of very educated, interested laymen. That's sort of what I have in mind for today. Would you mind explaining sort of the roots of GWAS, maybe coming out of the single, SNP research, the transporter polymorphism kind of thing in the early 2000s, and where we are right now, what we've done in the last 10, 20 years in this area?
Sure. So GWAS is where you basically associate an outcome with all of the genome, where, it's in scare quotes, all of, we'll get to that. And it indeed follows a period of time where they were like, well, that's really expensive. We can't really measure all of the genome in any sense. Like the first genome was only sequenced in 2002 or 3, and it cost like billions to sequence that one genome. So before they even did GWAS, they were like, well, but we know some genes, or we think we know some genes are very interesting because we have other biomedical research saying, well, dopamine is important or serotonin is important. So why don't we measure those variants in those genes first? So they would find the variant, and find one that sort of varies between people. So that's a part of the genome where we're not the same. And they would say like, okay, well, this one clearly is in, a dopamine gene and therefore it might be related to psychiatry. Let's go find out. And they tried to do that. And they seem to find success, especially sometimes like, oh, it doesn't really associate with a psychiatric outcome. But if we interact it with trauma or interact it with, parental income or whatever, then we do find sort of an association. And then people would, flock to that one association, try to replicate it. And, the usual sort of like great things about science that people can, try and replicate other results, but also the terrible things about science that only those replications that succeed actually sort of make it into papers. There's publication bias, all that kind of stuff. They kicked in. And you got this sort of like period of time where people would find like, the serotonin transporter gene interacts with trauma to affect depression. And there would be a paper and a replication and a meta-analysis. Maybe one meta-analysis said, well, we don't really see anything. The other one would say, we see anything. And it led to sort of like what eventually turned out to be a completely false positive association. And I think we could have gotten there earlier if we tracked the effect size instead of like whether it was significant or not, because with every bigger meta-analysis, obviously, whether it was there or not, the effect size was shrinking, because if you increase sample size, regardless of whether it's still significant or not, like, you can get closer to the true effect size, provided you have a reasonable, if you include all the studies there.
And there were voices for caution pretty early on in the literature as well.
Yeah, there were. And there were people like crying out that this was just all false positive as early as 2007 or 8. And I think the Behavior Genetics Journal at some point even said, like, we're not going to accept kind of gene studies anymore unless you have sort of like pre-registration, all kinds of stuff. Very early on, before that was even in vogue, they were like, look, give us a biological plausible mechanism and some other criteria before we even consider it, and a power analysis.
So we had these candidate gene research projects early 2000 that lasted for, I want to say 2018. This was still live and kicking for some reason. Until
it zombied on for a long time, and people still got like really big ERCs and R01 grants in the US, I guess, on these all the way up to 2015, which is like, as a geneticist, it was painful to see. But like, I think a large portion of the field pivoted to GWAS when, one, we could measure the entire, or a large portion of the genome, the portion of the genome that is frequently varies between people, so not very rare mutations or unique mutations one family might carry, or even like a few percent of the population might carry, but like the frequently varying part of the genome we could easily measure by, say, 2008 and 9. And people started doing what's called GWAS. So just take the entire genome without prior hypothesis. Now, this is really interesting in a sort of philosophy of science kind of way, because now, instead of saying, oh, we're doing 800,000 tests because there's 800,000 measurements on our chip to measure the genome, they said, no, let's just compute how many independent signals there are in the entire genome, regardless of how you measure the entire genome. So they did, before even doing the GWAS, they were like, our alpha, our p-value threshold will be based on the genome structure, how many independent sequence parts are there, not based on the number of tests. So there's no more cheating that, right? So you just do, if I were to do a GWAS and I omit a chromosome, say chromosome 4, because I'm like, well, I don't believe in chromosome 4. It probably doesn't have anything to do with psychiatry. No one would give me a free pass and say like, oh, you can have a lower p-value threshold. No, the p-value threshold would be an insanely sounding 5 times 10 to the minus 8, which is basically 0.05, but then accounting for the fact that there's a million independent tests, give or take, in the genome.
So very quickly in this area, right, 2013, the Heck et al. Study, I think I remember, was a null finding on depression. I cited those during my early PhD, so I remember those pretty well. And very early in the literature already, which is like 10, 12 years ago, people called for larger samples because they were testing an incredible number of associations, and they corrected for multiple testing. And so then you would have to have very strong signal for any of those SNPs to become significant. This wasn't the case for a while. I think Na Kai's paper, 2016, I want to say, found the first hit in the Han Chinese sample. Maybe that wasn't the case, but it was one of the
Yeah.
first studies. They found a signal in it for major depression in Chinese folks, only women, and I think only very severe recurrent depression. So they homogenized the phenotype a little bit, which makes working on the depression side of things, like me, quite happy. And then there on, we got larger samples, more significant hits.
Yeah.
And our study has 600, 700 hits in.
And so I think what's good for non-genetics people to realize is we call these GWAS meta-analyses, but they're different from meta-analyses in one respect, is that instead of meta-analyzing prior studies in the literature, right, which is the common way people do meta-analysis in psychology, you actually send an email or letter to all the cohorts you know have a measurement of depression. You tell them the design of the study. So we'll, quantify depression in these 5 or 6 ways. We'll find acceptable, these we won't. And, this is how we'll do the technical genomics part of the GWAS. This is how we'll upload our results to a central server. And this is how we'll meta-analyze those. It's sort of very close to pre-registration because you're actually sending it to 200 people. All of them are fairly knowledgeable. Some of them are epidemiologists, some of them are biologists, some of them are geneticists, psychiatrists. They all have an opinion. And before you even get anything done, they'll have a call with you where they basically disagree with many parts of your design for 2 hours and you adjust. And so basically that all happens before anything is done. Then they do the analysis and they submit their summary, their results, summary results to a central server, and then they're all analyzed. So there is no file drawer in that sense, right? All studies we know exist with depression outcomes are invited, and some of them might not opt in because they don't have the time or the manpower or whatever. But in general, there's no selective like, oh, I don't like that sample because like they didn't give me a result last time kind of stuff happening. It's just like they're all in.
You may have some selection bias, but it's minimal, and it
obviously,
it runs me from clinical trials. We have these IPD analysis, right? Independent patient data analysis, where you get you get the raw data, but even if you don't get the raw data, other people can carry out the analysis or contribute to the analysis based on the raw data rather than aggregate, which is classical analysis.
To push back a little on your thing about participation bias, these study designs do still suffer participation bias, right? So if I just have an opportunistic, let's send 10,000 people in the Netherlands an email or a letter saying, would you fill in a questionnaire and give us some DNA? I mean, there are studies that are, bit more rigorous than that, but they are like opportunistic. There's a big likelihood people that are very depressed will opt out or will just not respond or will have other things going on in their life. But that all exists, right? But then there's also Denmark, where they take heel prick blood from newborn babies, and there's only opt-out, not opt-in consent, which in their cultural relationship between government and populace is just something that's acceptable. And they just basically have almost zero dropout, and their phenotype is actually all the medical data the government holds on its populace, and there is no such thing as dropout. You can argue medical records aren't perfect measurements of depression, obviously, but there's no sort of like participation bias in those cohorts. So that's the GWAS, basically.
Right. So thanks for the little history, Michel's history of GWAS. It's 2024 now. We've had bigger and bigger studies and samples. And we're going to focus on depression today as a phenotype. Yeah. And so, where should we start? Should I throw a few things at you, or
go?
So the first thing that stood out to me, and maybe that's a bit unfair criticism because the paper is technically just a preprint and so forth, but it's a big consortium. I think I found 331 authors on the paper, if I saw this correctly.
Yeah.
As a depression researcher, I did not know what they measured in their study, which is a little weird because the biggest concern I've had about GWAS is the phenotype under interrogation. I think I'm not the only one there. And it's a genuinely hard problem, and it's probably not even solvable in any easy way. And I know that some of the consortium members also agree with this, and many of them have been working on better phenotyping. And maybe just the potential viewers here, there's the question is, what does it mean that somebody's depressed, right? And there's lots of literature on this. People have different definitions on this. And there is evidence that large genetic studies by Nakai, for example, right, in who's in Munich now, there's evidence that large genetic studies that sort of took a shortcut to measuring the phenotype of depression by, for example, taking the 23andMe, I think 2 PHQ questions or something, find different hits on the genome compared to studies doing like strong structural interviews by multiple clinicians.
Let's break that down. That's a really good start. So when you say 2 PHQ, that's just literally the 2 main domains of depression, right? That's sort of like, are you down? And the other one is basically, sort of, one is, are you sad and down all the time? The other one is basically, do you lack feeling? Like, are you just like, yeah. And then, and you're right. You asked me this question emailing back and forth before, like, what are the phenotypes? And I scrolled to the supplement, which it's only partly uploaded, and that's partly to some poor PhD students or postdoc will have to upload 200 tables in one format to a journal, different format to medRxiv. So I'm sure it will eventually populate. But yeah, the descriptive, which is super important because no one's going to scour over the tables, especially someone new or who doesn't keep up with every GWAS. The description is very insider baseball. It's like, oh, these cohorts, which they label by a name, like, the 49 core MDD cohorts, which to me means something to you, may not, are, phenotype like this. And you might be like, what are those cohorts? Like, where are they in the world? What part of the study are they, right? But basically, they do acknowledge your earlier criticism and that of many others like Nakai and I think Gantler and others, that like these aren't necessarily the same measurements. Asking someone literally in some studies, like, have you ever been diagnosed with depression? And in other studies, they're like a 2-hour interview.
Right. And this matters because we know that, for example, so 90% of the interviews in the world are unstructured. That means you just ask questions in a way that is sensible to you. And in the end, you try to get at these 9 core symptoms of depression or 2 core symptoms, 7 secondary symptoms. And the intervention reliability for this is pretty low. That means if you send the same client who's seeking help for depression to 2 different clinicians, they will more often disagree than agree. So it's about 0.28, 0.30. But for structured clinical interviews, the accuracy is more 0.6, 0.65. And that's why, of course, for a depression researcher, to me, it matters to find information on where most of the, and again, they talk about this in the supplement a little bit, but then they refer to a supplement that's missing. And that's why this would be important to solve, because for any GWAS, I think the question is, what are these SNPs exactly for? Which I also want to talk about later in terms of covariates or other overlapping phenotypes, stress, life events, neuroticism, right? All these other things that might have similar SNP loadings on the phenotype.
Yeah. And so they do one thing to accommodate sort of this heterogeneity in phenotyping. They basically split up the GWAS into 4 primary analyses. One is based on questionnaire measures of depression. One is a meta-analysis of like self-reported diagnosis, like, I have been depressed in my life. One is like real clinical interviews. I don't know about structured or not structured, but like at least clinical interviews. And then the final one is electronic medical records. I think that's mostly separated out because not all electronic medical records are equal, right? Some of them are really a psychiatrist after one of those interviews deciding they will give you a diagnosis. The other one is just maybe a GP ticking depression during a referral, right? So what a medical record means, or even like you're in an EHR and it becomes very clear to the doctor that you have some sort of like depression-like thing going on, and it will tick it and send you on your way for like, don't just leave it at this, go see someone for help. And so, they separate them out and they GWAS them. And then they say, well, these 4 definitions, they genetically correlate between 7.78 and 0.88. And I think the easiest way, if you don't know what a genetic correlation is, to think of it as a correlation, but not between the traits themselves, but between the genetic risk to the trait. So like every trait is binary or whatever, and underlying it's like little normal distribution in terms of risk. And those correlate like between 0.78 and 0.8. That's high, but it's not 1. And these are big examples, so it's very much not 1 in terms of like, if you want to test it, it's high, but it's also interesting to note that like the genetic correlation between bipolar disorder and schizophrenia, which many psychiatrists would tell you, yes, there are features that they share, and there are parts in someone's life you could say, well, you're manic, I don't know which one it is, or you're, might be hard to see which in a moment, but if you interview someone about their life, those are very different things. Like and they correlate 0.7, right? So these definitions are similar. They're definitely more similar than they are to other disorders, but they are not identical. And they try to accommodate it.
Is that consistent with the previous literature? These 0.8 genetic correlations?
Oh, it's in the paper somewhere. It's in a ad-lib sentence in the middle, 0.7, A2, 0.88.
Is that consistent with what Nakai and others have found previously? Do you know?
I think it is. And I think one thing that's different from the Nakai effort is these are more like, by necessity, this is like the top level paper. I'm sure people will do more work with these data as they come out, right? As the data becomes shared, I think they're uploading it now. These are very high level aggregations, right? yes, you can see sort of like a single question, have you ever been depressed, or a questionnaire, are different things than a clinical diagnosis, but they're still very high level. And you could say, well, why don't we split by age? Why don't we split by sex? So they made their choices, which already makes things more coherent, so to say. Like if there's a big male-female difference, right? All of these definitions combine males and females, and so that will be lost.
Right.
And so there's nuance lost here. That's absolutely true.
Okay, then let's take a second to say thanks for uploading the data, because unlike some other fields, this field has taken quite a bit of money out of the research community fund, I think, and some have seen this quite skeptically in terms of sort of improvement for patients, but this community has been awesome in sort of pushing the boundaries of open science, I think, from at least from the sidelines, from what I see. Data sharing is common, collaborations are common, big consortia are common, which is much better than having 1,000 tiny studies, right? Kudos.
And usually they're like open at preprint, right? I don't know if this one's up yet, because it's like, I think in total there's like a many underlying small GWASs, right? So uploading will take a while, and sorting out all the privacy, because there are genuine privacy concerns. You can't upload someone's genome without further sort of control on that. That's just like not a thing we can do in our field. But usually they're like available between preprint and paper. So it's not even that people wait till the paper is accepted. People can get going. And if you're just asked to collaborate, then you will sort of adhere to the embargo that at least the paper has to be published. You can get the summary statistics now under collaborative agreement. So it's not that's good.
Can we briefly stay with the genetic correlations, Michel?
Yeah, sure.
So is that an upper bound at 0.8? Is there anything like the correlations I know can be adjusted for third-party variables or covariates, so to speak, and then you get a more sensible estimate. Does it make sense to adjust in the genetic correlation between different phenotypes or different types of measuring depression for other genetic phenotypes in the covariate sense, or is that not sensible? Is the 0.8 sort of the upper bound or the lower bound, or what are we talking?
It's like it's not a partial correlation in any sense, right? It's sort of your upper bound. They're not going to get more similar unless you find something that like negatively affects clinical diagnosis and positively affects sort of like the self-reported diagnosis. That in controlling for that would push it up, but I would say that's a kind of neither here nor there. Like sort of like this is the correlation between these two things, unadjusted for anything basically. Adjusted for all kinds of like genetic kind of types of confounding are taken care of very well. The fact that the samples overlap, it's all taken care of. That this is a good estimate of correlation, but it's an upper bound. Like these, and it's pretty high,
It's very high, yeah. So let's go back to because that's one of the concerns I've had with this literature for some time, and I didn't fully grasp this problem, and I think it's related to the genetic correlations. So we have a phenotype here, depression, that is measured in various ways, but the authors show pretty convincingly that apparently doesn't make that much of a difference how we measure it. And then we find SNPs or alleles that are correlated to this phenotype in a way. And we know there's probably some level of causation because probably for most folks, their genotype was before their depression onset, right?
By definition, it has been. Yeah.
So now what neuroticism and lifetime episodes of depression are correlated, I want to say 0.4, 0.45 at the phenotypic level. To what degree does this paper, are these SNPs for depression, or are these SNPs for adverse life events, for being vulnerable to responding to adverse life events with mental health problems, broadly speaking? Are these SNPs for neuroticism? How does it work in GWAS analyses?
So in GWAS, you should see the correlation between a SNP and a phenotype like depression as any path through which the SNP may travel. So for example, if people with like sustained pain issues, nerve pains, back pains, become depressed due to that, then they will enter the case pool, especially in the have you ever been depressed or questionnaire style things. Like maybe a good psychiatrist will go like, well, I'm not going to give you a label depression. I will treat you with an antidepressant because currently you're in a depressed state, but you need to be referred to a neurologist to solve the pain thing or the sleep thing or whatever thing, I think, or hormonal thing. Because then if you then still are depressed, come back to me and we'll work on it, right? So that's like good clinical care if in the way we hope it would like be always applied. But in general, and even then you might be diagnosed with depression to facilitate the treatment, right? And so because you actually are depressed at that point, right? But like all those people end up in the case pool for a GWAS like this, which means that like any way through which the SNP acts on depression, to
That's
very, very distal things, it will end up in here. And that will translate into genetic correlations.
right. So I love that language. So you're saying now, and I have thought about it like this before, but not exactly in the way. You say there are SNPs on the causally origin side of things.
Yeah.
They all contribute to unknown, in a way,
Yeah.
causal factors. There's this big pool of stuff. And then actually a lot of these SNPs, we know them to be transdiagnostic, hence the genetic correlations are pretty large between phenotypes. They come out in some side and then they are associated with phenotypes, but we don't always fully understand, and the authors get into this in the paper to some degree, I think, we don't always understand the exact causal pool, whether this is mediated by pain or goes to personality types or vulnerabilities to environments, or specific neuroreceptors that convey vulnerability for certain pathways due chemical imbalances and so forth. So that's pretty unknown, I guess.
It is pretty unknown, but we're getting to place. So let me give you an example. Like, imagine a model where depression is just purely a function of not being treated well by society, not being treated well socially. Now, that wouldn't necessarily be heritable, right? So, whether treated in any, well, I mean, insofar as it is, that can also exist. But imagine among the people that end up depressed because society doesn't treat them fairly are people with disabilities, physical illnesses, and, they're just left out, their treatment isn't going well. And imagine that world. In that world, the genes that would contribute to depression would be associated with those physical ailments, like, blood pressure regulation. And due to that not being treated, they will end up. And so you can imagine a model. I think there are people that actually, this may be an extreme model, that are like, well, depression isn't necessarily a disease in itself. It's really only maladaptation to society, not indeed helping people deal with their other problems. That could be a world. But like a counterpoint to that, not a full counterpoint, but a bit of a counterpoint here is that, like, actually the genes that associate with depression, they're all genes that are expressed primarily in the brain, and then within the brain, primarily within neurons. Right? So, which speaks against it purely being a function of other things, other ailments, right? So it's sort of like, not saying the body doesn't influence your psyche, because that could still also be a thing, but like, it's not just that. And so we can get parts of the way to causation. And to be entirely honest, because we're now painting a fairly rosy causal picture of like SNP goes to alcohol, there is one big exception. You carry the same alleles as your parents, right? And your parents' phenotypes, or the way they are, their personality, it shapes your childhood environment, right? And so there's this other causal path that could arise. The gene that's in you, it's also in your parent. And it can influence your outcome through actions of your parent. A really great example of it is like if you GWAS birth weight, like the weight you have at birth, and you do a genetic correlation, you get a genetic correlation with smoking. Now, that's not the fetus smoking, right? That's the father as an environmental exposure, and maybe the mother smoking during pregnancy. And so this could also be the case in depression. And people have tested it by just comparing between siblings who share a mother and a father, right? And so it doesn't appear to be a huge part of what's going on with depression, but it's important to mention.
Right.
We are interested in SNPs because we want to study the causal path that goes from like biology to the trait. And I personally think that path might go through all kinds of social like things, like, oh, you're in pain and our society doesn't care for you well enough, or it's just an unresolvable kind of issue, and that will lead you to, that could be part of the path. Others want to dig into the biology, and this comes to where, we're all doing this GWAS because we needed to do further studies, but it doesn't mean that we all think the same causal mechanism lies between SNP or genome and depression. But yeah, that's sort of the way this gets together.
I have a thought about the causal pool now.
Sure.
Because now we're getting to, not necessarily, you might have seen this, I talked about this a bit with some colleagues, or I got some advice from colleagues about the explained variance and how this translates to causal impact in terms of intervention power. Yeah. Because the authors in their paper, again, I have some friends on this paper, but I'm still going to read that main quote. These findings represent a major advance in our understanding of major depression across global populations. It's a pretty big statements there, that a single paper is a major advancement. Yeah, folks have been on this for a couple of dozen of years for quite some time. So let's talk about the R squared. The R square in the paper is about 6%, and the authors provide an upper bound of R square, which I wouldn't get away with in my phenotypic work, providing an upper bound of an R square in a abstract. So what does it mean, and how does it translate into potential clinical utility? Because in my layman's understanding of R square,
Mhm.
uh, the lever seems pretty small if you can explain only a small portion of the variance. But I understand now that this doesn't necessarily need to be true.
Okay. Let's break it down, right? So what the R square means is they take the results of this GWAS, which for every sort of common variant in the human genome carries a beta, like its effect on MDD. And then they take people that aren't in the discovery GWAS, that are out of sample, and they predict their status, yes, no, whatever the diagnostic criterion in that outcome sample is, and they compute an R square. And then, because the outcome is binary, they have to do some math, but it's basically a squared correlation, right, between the polygenic score, so the score based on your genome and the external GWAS we have, and your risk for depression. Now, it's not that much. I agree. It's 6%, let's say. And I think what they mean by maximum here is that we'll reach 6% in people with a European ancestry. It will do far poorer in any other ancestry in the world because their genomes aren't represented well in these studies, right? And that's just more a technical genome thing than anything to do with ancestral differences. It's just like we designed the way we measure the genome initially, not for a diverse world because the money is in the West and that's where all the research
Have
sort of
more
happens.
power to detect a correlation or predict R square accurately in Europeans. We have more data there. Therefore, the 5.8% works in Europeans is an upper bound, but it's going to be smaller in populations with smaller sample sizes. That's the nature of GWAS. That makes sense to me.
It's the nature of prediction if you don't have a good sample to develop your predictor in. Now, it's low. That's one way to look at it. 6% is not that good. That's not that high. There's two arguments to be made here. It can still be useful in certain settings, right? So if you, for example, they do a plot where they compare the lowest decile of risk, so the 10% of the target population with the lowest risk and the highest risk. Now, it's a bit of a cop-out because that's only 20%. What happens to the rest of the 80%? But let's stick with it for a second. They say, well, the odds of being depressed is 5 times higher in the highest decile than in the lowest decile.
These are people who have lots of these 700 risk alleles, so to speak.
Yeah,
right?
or they even include other alleles that aren't genome-wide significant. But yes, they have a lot of them, and the other one group has not that much of them. And that would be like going out into the street and seeing who has a high risk of depression. But like a great psychiatrist friend of mine who also studies in this field, if we can include like links, I'm going to do that later. But Wouter Perot actually said, well, that's not necessarily what we want to do in psychiatry. He's like, I'm a psychiatrist. What I want to do is I get people in my critical care clinic. They have a depressogenic presentation. And like before they get to this clinic, it's in Amsterdam. It's sort of second line clinic. So it's pretty bad, but I don't know whether they have the kind of depression that will become a depression or might become bipolar at some point, or they might become, might develop schizophrenia. Usually, so the prior odds aren't like you have no depression, 80% chance, or you have depression, 20% chance. They're like, you have none of these, but you're just like distraught due to exogenous things, like something horrible happens to your life, 20%, 30, 40% depression, 10, 15% bipolar, and another such number for. And he shows in the paper that, well, actually, if you take these scores that aren't that predictive in terms of like variance explained, you take those priors and you compute the posterior risk given people's risk for schizophrenia, based on that GWAS, MDD, bipolar, and maybe some other psychiatric GWASs, and that's even prior to this one. You can actually get like a really pretty high reclassification where you can say for like a substantial number of people, like I don't want to quote numbers out of context, but like a substantial number of people, your risk of any one of these is higher than 60%. And that becomes actionable in the sense that if someone has a very high risk of bipolar, there's other psychoeducation. It doesn't even have to immediately go to medication. There's like things you need to be aware of. Things that mean you're going into mania.
So you're saying this PRS, this score everybody could get, which is a number, it's information on how severe your risk is, and that could be actionable for some individuals if we were to do GWASing at large at birth, for example, like maybe the Danish folks would do.
It's more that in certain settings where your prior probability of having any one of a number of outcomes that are correlated but not identical, right? So in psychiatry, that's very common. You come in with like these presentations. For that group of people, it's predictive. Whereas I don't want to go into a school genotype
Right.
everyone and go like, you guys have higher risk, but the risk is still only, might be very high. It might be 50%. What do? You freak them out, go like, you might get depressed. I'm sure that won't have the effective effect. That's the thing you could consider in terms of like unactionable phenotypes. Like imagine breast cancer screening, right? You might screen certain people in a mammogram earlier than others, but like for depression, where we don't really have a preclinical intervention that we know to prevent depression, what's the point in scaring people?
Yeah. So there
It should
is
be application
ethical
domains.
considerations and also privacy considerations that have been discussed in
Yeah.
other settings. As you know, I'm building an early warning system for depression. And so, of course, if a substantial proportion of my participants would have a PRS score, which is not possible by
Yeah.
definition, because it can't be a substantial one that is enriched in PRS top 3%. But of
Right.
course, it would change my models if I would knew that these 3% of my participants are exceptionally, like 5 times more likely than the other participants, for example, given at the end of the spectrum, to develop depression. And we know that peak onset is, 19, 20, 21, and this happens to be their age. We could pay more attention to those in our early warning. We could, measure them or whatever. Like
right. If you work with things like apps, right, where they get triggers to fill in questionnaires, you can imagine having one of the sensitivities of the app being everyone's annoyed by pop-ups that they need to respond to. But in some cases, you maybe want to be slightly more invasive because you think the prior risks are higher. That could be a thing.
So I need to do skin cancer screening because I'm pretty pale and I was pretty sunlight exposed when I was young. My parents, we went to Italy by car because that's really close to southern Germany, right? And so I go every year to the dermatologist, get my skin screened because I'm higher risk for multiple reasons, also skin cancer in the family. And you could envision something. So I'm still in this pocket of the discussion because I'm curious how to get from 6% R square to this has major implications for, prevention and treatment, which is either said specifically in the paper or the authors allude to it. And I've heard this about the field a little. And so I wanted to better understand what the actual clinical implications could be. And one example you gave is to say, once people already have passed a certain threshold, they are in the clinic, for example, I can adjudicate a lot better. Having
quicker, earlier in the process. But these are all potential. These are still pie in the sky, kind of. But like the 6% is just one number, and this other thing that's more specifically, someone gave there's this gene. I'm going to take us on a slight detour here. We have a few more minutes. There's this gene that is sort of like explains 4 or 5% of variance in Alzheimer's risk, ApoE. Right. And one way to look at it is like, well, then where's the other 95% of risk? But someone did this really interesting epidemiological study where they said like, well, but if we sort of consider the gene causal, right? And there's 3 alleles, like low risk, middle risk, high risk. And usually people say, oh, middle risk is this percentage of people get Alzheimer's and high risk is this other percentage. But they said, well, no, if you want to know the effect of this gene in terms of like, if we were to alter its effects on Alzheimer, we can't do that yet, but if we were to be able to do that, what would be the gain? And they pointed out that, well, if everyone carried the lowest risk allele, which is fairly rare for a number of reasons, then actually that would prevent 75% of all Alzheimer's cases. It doesn't mean it's the only cause of Alzheimer's. There may be other ways and other pathways, environmental and genetic, but just blocking this specific gene pathway. Now, let me just, before people think we're going to solve depression this way, just point out that this gene's effect is so big you could find it in small GWAS. There are no genes to date, and it's not likely that they'll be common if they exist with this kind of effect on depression, right? So we need 500
orders of magnitude away from that, right? Like we're really far away from this.
Really far away from discussing that. So intersecting but like it doesn't mean that because one of those SNPs or one of those genes which a SNP lives has only a small effect. Like I think one of the top hits they find, it lives in dopaminergic, very well understood dopaminergic genes. The fact that one SNP explains like 0.1% of variance doesn't mean that if you would interfere on that pathway effectively or more effectively, even that it wouldn't sort of like be actionable. But in fairness, compared to GWAS of bipolar disorder and schizophrenia, which are slightly more heritable, where the effects are smaller on depression. And I think the point you make about the measurement, it does come into it. It's just harder phenotype to recognize, to get psychiatrists or clinicians to agree on. There's many reasons that might be the case. It's probably diluted because we're including all these other phenotypes. And maybe, sometimes we internally discuss, like, maybe the next step isn't again bigger. Maybe the next step is keep it this big, but make the phenotypes better. And it may mean you need to drop some samples.
Right.
But so far, the cost-benefit trade-off has been to like, no, just get more in, you know?
So then I have a detour too.
Yeah.
Riddle me this, Michel. I worked with Randolph Nessy during my PhD, who's an evolutionary psychiatrist, and he sort of has always asked, I think, the right questions, and he has also often given the fantastic answers.
Mm-hmm.
And he and other people in the field have always asked if there are single genes that are not just de novo mutations, but they're genes that are heritable, that are carried by considerable portions of the population. Why do they persist if they impose selection pressure? Now, the easy answer for this, of course, in terms of aging diseases is, well, people didn't get 65, so genes couldn't be selected for. That's why I have no hair, probably, and other. But there are other genes too, right? Who have like schizophrenia genes who have impact in adolescence already. Why are they retained in the genome if they're heritable and if we would expect them to have detrimental costs to fitness? And we know that 0.1% fitness cost genes are usually kicked out of the gene pool after a couple dozen generations already, at least in simulation studies or bacteria and so forth.
That's a really great question, and it comes to one of the disconnects. So what we're studying here are very common genes. That's what a GWAS does. So if you want to study rare genes, you need to measure everyone's genome entirely 20x, more than 20 times, because detecting rare things, the error rate is far more important. Because if you make an error, is it a rare thing or is it an error? Hard to distinguish. So those studies also exist. And what we learned so far is that, the genes with big effects on any psychiatric outcome, whether it's depression or schizophrenia, especially things like schizophrenia, which people who suffer from schizophrenia have less children. That's widely observed effect, right? Especially males, but also women. It's just staggering rates of having less children. And all genes with large effects on these outcomes are rare. It's not because rare variants somehow magically have higher effects. It's just because they cannot become more common. If they were to become more common, they would be selected against by people having less opportunity in society. And it's not like some sort of biological process necessarily. It's like if the society is inhospitable to raising a child while you're suffering psychiatric illness, then that will be enough to sort of make it be selected out of the. So that doesn't need to be a biological process. It can be a social process.
So you're saying these genes are there, they're at the margin of the distribution because they lead to having fewer children, and
they're rare.
They're rare, and they persist because
they persist a couple of generations, but they're selected against. And so what they do in a rare variant study is interesting. They have a gene, and they sum up all the mutations that they can predict. They don't do a per SNP, per variant association, because they're so rare. Only a few people in 100,000 carry them. They aggregate those that are in the same gene, and that are predicted to perturb or break up the protein that the gene codes for. And we can do that because we can see this genomic code would translate to this protein, and if we change something here, we will break the protein. We kind of can get at that. So they aggregate them and just find all the and they can do simple things as saying, well, this gene doesn't have any rare variants.
Right.
And what that means, no one was born. No one survived up to childbirth with those variants, right? The gene is so important, any variant that wrecks it will be non-existent. And so that does exist for psychiatry, but the ones that persist to become common, their effects are so small that they are kind of survive selection.
Right.
And that's what we're looking at. We're looking at the variants that are of effects that are too inconsequential to really be efficiently be removed by natural selection or any other kind of selection. So these are the things that aren't that important. And that's sort of a catch-22, right? They're easy to find, but they can't have big effects. So, but surprisingly, that's where most of the heritability lives. Most of the heritability of these traits lives in variants that are, they are affected by selection, but only in a very minor way. But
I have one last on my list of FAQ Michel questions, but I'm not sure if you have anything else to talk about before I wrap this, because I wanted to talk about case control studies generally, of which GWAS is one kind of.
Sure.
And I've been working on this for some time, and I think there's growing agreement in the field. If we agree on so much, but people don't like the DSM anymore.
No, they don't.
People don't like case control studies anymore because there's sort of really agreement at this point in the literature that the phenotypes we study are not bins where people are
No,
identified in them, right? And
no,
that is maybe less so for some phenotypes than others, but
yeah,
it's pronounced for depression, right? You know that, and
sure.
people work
Yeah,
this
it's
know that,
harder
and
to.
take it
Yeah.
very seriously, right? There's tons of heterogeneity within this pool of MDD cases that are put on the one
Mhm.
side of the GWAS study, and then there's also heterogeneity, but a different kind in the healthy controls on the other side. And so,
Mhm.
is there any way that GWAS studies, there was work 2017 already I read, but
Mhm.
I didn't fully understand the modeling. Is there ways to get around this case control thing by looking at dimensions from very underpressed to very depressed by, having
Mhm.
some sort of continuous outcome score,
Sure.
or is that not possible because you guys really like your logistic regressions? How does it work?
It's not that we like logistic regressions. Actually, we analyze case control data with linear regressions because, like, I'm gonna be this is gonna be if anything of this gets into Twitter, cut this out, right? OLS is fine. You know why? Because the effects of the SNPs are so small, they can never really push people outside the probability space between, and this is going to be really technical, between 0 and 1. So for our case, whatever. I don't know. People do logistic regression because there's like subtle neatnesses about it, but whatever. Anyway,
But your outcome is binary, right? You predict the status of either being depressed or not
yeah,
depressed using a SNP.
yeah. But like the probabilities of being depressed in like the three states of the SNP, like allele 1, both alleles, mostly
Oh, I
allele
see.
2, those are all far between 0 and 1 because the SNP has small effects. So you don't need to switch to logistic. There's other reasons to do it. We don't want to go into that one. Anyway, here's what the breakdown I give you. There are continuous measures of depression. You can do GWAS of them.
Okay.
They're very useful. Selecting those cases with severely affected depression that some people like Ken Kendler believe are like, more focused type of depression, that has its own uses. I would argue that instead of going, why don't we rechange the entire phenotype and redo another GWAS of 5 million people, which would take a lot of time, right? The thing we can do is use the GWAS we have now to learn about heterogeneity. One of the most fascinating heterogeneities I found in the depression genetics literature is the genetic correlation between depression in Asian ancestry individuals who are predominantly in Asian countries and Western individuals who are predominantly in Western countries. Now, the difference could be culture. It's cultural, right? So we're taking account of all the biology here, but the genetic correlation, taking account of all the sort of the mechanistics of the genome, is like 0.45. So whatever depression is, whether it's in diagnosis or in cultural definition or is different in those two samples. I don't want to generalize to those cultures, but it's something to follow up on. Why is the
Right.
genetic correlation between depression in England and the Netherlands or England and the US very high, but it's far lower, with Asian countries? Could be diagnostic systems, could be definitions, but like we can take things that are very different, depression in men and women, we can genetically correlate them. So you can take these genetic results and go study heterogeneities that way. So that's why what makes me so excited about genetics of depression is that maybe it was in some people's minds a leg up to biology, to finding a drug or whatever. But genetics is almost it's agnostic towards the mechanism. It's just the SNP goes through some pathway. It might be mostly after, a bit of biology in the beginning, because, that's how SNPs act. It might be mostly cultural, that pathway, right? If you were to do a GWAS of lung cancer in Europe prior to Columbus going to the Americas, you would not find the biggest hit we find today for lung cancer, which is obviously in the nicotinic receptor gene, right? So
Right.
imagine us looking at this GWAS. We look at the top hits and we go and try and find the drug. It may be that is very much like the nicotinic receptors gene effect on lung cancer. That no drug, once you have lung cancer, will prevent the effect of having smoked in the past. We don't know. But that also gives us opportunity. It also means we can use those unknown causes of depression, which we are all interested in, and do comparisons across culture, across age, across, diagnostic system. I know some economists who were like, what if they had a data set where there were like DSM-based diagnoses and there were ICD-based diagnoses of the same people, because sort of like, and some people shifted because there's like imperfect matches. And they were like, why don't we use genetic correlations to figure out the best way to map, ICD to DSM? Like, what are we doing wrong? Where are we sort of like
Right.
because by just like the fact that we're taking people that are in one diagnostic bin and DSM and we distribute them differently in the ICD, that would carry the genetic correlation.
Right.
And so one of the things I've been working at, and that's maybe a nice one to stand up, what I'm working on with respect to this is I want to get the field trial data for the ICD-10 or the DSM, where basically we have, so field trials, the following thing. You have a new diagnostic classification, they give it to a lot of psychiatrists and psychologists and clinicians, they train them, and then they have them evaluate the same patients. And then per patient, like they only report on like the consistency for the diagnosis because that's their goal, right? But what I'm interested in is when one clinician says depression, what does the other clinician say? What's the marginal distribution of the other clinician? Many will say depression, but they will also say other disorders. And the thing I can imagine, what I now want to do with that data is go like, what if there's no correlation between the disorders and reality? Right? Imagine all the DSM correlations are not genetically correlated, but there's only diagnostic error in certain directions. What genetic correlations would I observe on that data? So you can really do interesting things with the genetic data. You can go like, okay, what would this misdiagnosis result in terms of genetic correlation? What would re-diagnose or whatever? And so those are very interesting questions for which we can use genetics. They aren't all biological. They aren't maybe going to reshape what we think of MDD, but I'm kind of psyched about being able to go to Denmark and correlate depression GWAS in the 1950s with a depression GWAS in the 2020s and go figure out whether those are the same. No one's done it yet. Someone please steal the idea or go do it. But like, are the diagnoses we made in the 50s the same as they are now? No. But like, how do they map? Are those depressed people still in the depressed bin, or did they end up in a different bin? So you can like imagine the flow chart, right? From like DSM-3 diagnosis made in the 50s. How do they flow? How do they correlate to like now? And that's things we cannot do without the genetics to link across time. Anyway, this was the positive spin.
I really loved your example. So I went into this with a learning goal, right? And sometimes examples in this literature can be really helpful to convey a message. And I will remember forever your example with the smoking baby. I think it's such a powerful example of the genetic hit being biological in that sense, or pointing at a biological mechanisms, but pointing at the parent smoking, which impacts birth weight. And that doesn't have to be the standard outcome, of course. There are definitely physiopathological pathways in the brain and so forth. But I think it's a really nice idea that you have this sort of biopsychosocial take on SNPs and their causal pathway into this pool of unknown, which then impacts in some way. I like your way of saying it. In some way, it ends up impacting the phenotype, and that can be through multiple mediations. Some of them might go through the environment. That's
I
really
fear the time where we're going to do all this mediation with genotypes. Like my old buddies in the methods department are not going to like me doing all this mediation.
Oh, well.
Anyway, I think we have to wrap up because we spend an hour doing this.
Thanks for chatting.
Fun. Let's do this again for the next paper. I want to find one where I can ask you a lot of questions. So if I see one of the network or dynamic EMA papers coming out and I'm like, wait, what's going on here? And they claim in their abstract that it's like going to revolutionize depression, I will make sure to like send you an email and we can do this again. How about that?
We'll do that.
Okay. Enjoy your holiday and see you on the next call or meeting. Yeah.
Hang in there. Bye.
Bye.